First, we'll get set up from the current slide. And my last announcement, and it really shouldn't be an announcement, but it almost feels like it should be this term. According to my locator card, on Fridays, I'm on the Birmingham campus from 7:45 to 11:45. However, last Friday I had a doctor's appointment. The Friday before that I had professional meetings. The Friday before that I had an infusion. The Friday before that I actually was at the Birmingham campus. But then 3 Fridays before that I had infusions then too. So for the last 2 months almost, I've only been there 1 time. This Friday, I'm back on Birmingham campus unless something comes up that's really weird. So I should be there from at least 7:45 to 11:45 with this exception. I saw an email last night reminding us of some big meeting that required attendance this Friday. But the email didn't say what time. It was a reminder, and the earlier email had an attachment, but it didn't come through because they didn't do it well. So I couldn't find the attachment. I've seen the email sometime in the past, and I just don't remember the times for the meeting. So sometime Friday I will be in a meeting. I'm guessing for at least an hour. I don't know if it's in the morning or the afternoon or morning into afternoon. I just don't know. But I'll try to find out by Thursday if I can. So I'll let you know what times not to try to come by on Friday. All right. Any questions on anything we've done up to now? Through already? Wow. Must have been an easy test. Huh?
Yes, kind of. What's up? Yes, sir.
Thank you. Oh, my goodness. Yes.
Thank you.
Okay. I thought I was just kidding about you being through. Okay. Way to go. Okay. Okay. So no questions? All right. We're in Chapter 5. That's Analytic Trigonometry. We're in 5.3, Solving Trigonometric Equations, and page 365, a nice round number, is equations of the quadratic type. So that's what we're going to start with if there are no questions. Okay, many trigonometric expressions are, equations are of the quadratic type. Ax squared plus bx plus c is equal to 0, except instead of x's you have trig functions. So for instance, this would be one in sine. 2 sine squared x minus sine x minus 1 is equal to 0. Or in secant, secant squared x minus 3 secant x minus 2 is equal to 0. 2 sine. What they're doing here is writing this in another form. This is with the exponent following the function, which is how I usually write it. This is taking the function, put it in parentheses, and putting the exponent by this. These two are the same thing. They mean the same. But this is just showing this is treating the variable x like a sine function. Okay? But we usually rewrite it like that. Same with secant there. What they didn't do, they didn't put parentheses around this sine x. I guess just because it was a 3 in front of that, they put it around secant x. To solve equations of this type, you do the same thing you did for this type, right? You use factoring if you can, and if you can't, you can use the quadratic formula. So it's perfectly fine to do, only now rather than x, you're solving for sine x. Once you get down to sine x, then you can figure out what values of x will make that true. Okay? So to solve equations of this type, factor the quadratic, or when that's not possible, use the quadratic formula. All right, so here is example 4 on page 365. Find all solutions of 2 sine squared x minus sine x minus 1. That looks familiar, doesn't it? On the interval 0 to 2 pi. Counting the 0, not counting the 2 pi. So this is a semi-open, semi-closed interval. Okay. So what would you do first? You tell me.
What would you try first? What's the F word? Factor. Okay. Whoa, let me get my pen color back. Okay. We are hoping this will factor. It may not. Okay. Now, time out. If that's not equal to 0, you don't even try factoring. Okay. But since it is equal to 0, we try factoring. Okay. Now, what is the only possible factorization of 2 sine squared x? 2 sine x times sine x. Exactly. I can't write it. Okay, there it is. Sometimes when I go to write sine x, I write 6. So I don't know why. Okay, where do we look next?
The sine of that last term. What is it? What does that tell you about these two signs? They'll be opposite. One positive, one negative. You have a preference? Positive first? Okay, we'll try positive first, negative next. Now, what's the only factorization for 1? This is hard. 1 times 1. All right. Now, let's see if we did it right. Okay? It may not be. We may need to move the 2's or change the signs or something like that. Let's see what happens. Let's foil it to see. 2x times 2 sine x times sine x is 2 sine squared x. Yes, we knew that was going to happen. And then we'll do the outers. That would be 2 sine x times minus 1 is minus 2 sine x plus sine x. That sure enough is minus sine x. And then with minus 1, we do that was going to happen. So yes, we got it right the first time. Okay? Good for us. Now what do we do? We got it factored. What do we do? Okay, yeah, because that's why we had to have that equal to 0 at the end, so you can use the zero product principle. So either 2 sine x plus 1 is equal to 0, or sine x minus 1 is equal to 0. All right? Now what? I did what you told me to. What do I do now? Okay, how do you do that? Say again?
You subtract 1.
I can't hear.
You subtract 1.
Oh, subtract 1. Got it. Subtract 1 from both sides. And what does that give us? 2 sine x. Those go to 0 is equal to negative 1. And then what? Divide both sides by 2. And now we have that sine x is equal to negative 1/2. And we're going from 0 to 2 pi. Now, where in that range of x's is sine x equal to negative 1/2? Now, here's how I would approach it. Where is sine negative? First quadrant? No, nothing's negative in the first quadrant. Second quadrant? No, sine is positive in the second quadrant. So the only place it's going to be negative is third and fourth, and then you're around to 2 pi. So we stop. Okay? So, in the third quadrant, is there any place where sine x is negative 1/2? Well, let's just take the reference angle of what is the reference angle whose sine is 1/2. Give it to me either in degrees or radians, I don't care. Where is the sine equal to 1/2?
40.
Say again?
45.
No, 45 is square root of 2 over 2. Remember the little rule for sines? I'm going to do it in the first quadrant, but it can be in any quadrant. Here, it's the square root of 0 over 2. Sine of 0 is 0. Here, it's the square root of 1 over 2, which is 1/2. Here, it's the square root of 2 over 2, that's 45. Okay. Here is the square root of 3 over 2. I can't write. And then up here, the square root of 4 over 2, which is 2 over 2 is 1. Okay? Those are the signs for those values. And we're looking for, we're at 1/2. What is this angle here? There's your 45. This is your 30. Now, if we get that into radians, what would that be? Y'all are old hat at this now. What is 30 degrees in radians? Here's a hint. Say again? Okay, here's a hint. How many degrees is it from there to there? Say again? No, here. Here to here. Right at it. How many degrees? 90. So this is a third of 90, right? How many radians is this? Pi halves. And what's a third of pi halves? Pi 6, exactly. Okay? So that would be x equal, but not pi 6, that's the reference angle. You're over in the third quadrant, so swing this on around. This would be pi, and you're 1/6 more than pi, right? Pi 6 more than pi, right? So that would be how many? 7 pi 6. So x is either 7 pi over 6. Where's the 6? There it is. Ooh, why did that do it? Okay, or you could be in this quadrant, remember? Pi is also negative over here. Where are you there? (11 pi 6). So this. Whoa, why did I put a square root on that? Goodness gracious, the old gray cells are losing it here. That's 7 pi 6 or 11 pi 6. Okay, so that will take care of that one. Can I erase this now because it's sort of in the way? All right. Okay, but you see how we got it? I don't know if that's how you like to see it, but I like reference angles. They're just sort of fun, you know. Okay, so we had that there. So let's do the second one. Sine x minus 1 is equal to 0. What do we do to solve that for? First sine x, and then we'll later solve for x. What we say again? Add 1 to both sides, and that gives us sine x is equal to 1. Okay, because this goes away. Okay, now where is sine x equal to 1? When x is somewhere between 0 and 2 pi. Where is sine x equal to 1? What value of x? It's what?
90 degrees.
How many?
90 degrees.
90 degrees, exactly. And how many radians is that? Pi halves. This will be true, x equal pi halves. Okay? Now, here, I just would like to picture my sine curve. Here we're starting at 0. It goes up to 1 at pi halves, then down to 0, down to -1, then back up to 0, and we've reached 2 pi. That's the one and the only one place where it's equal to 1. So, here is our solutions. Pi halves, 7 halves pi. Here I tried to write a square root again. 7 pi pi 6, sorry about that. I'm having trouble writing today. I don't know why. 7 pi 6 and 11 pi 6. Okay, those are the three angles between 0 and 2 pi where that quadratic function is fulfilled. So what we do, we factor it, just treating the trig function as if it was the variable. Then we solve for the trig function, and once we have it solved, then we figure out what the x is. So it's just one more step from what we usually do with quadratics. Okay? I'm going to go and erase all this unless someone has an objection to that. You got it? Okay? Then let's see how they did it. Well, they treat the equation as a quadratic in sine x rather than in x, and they're going to factor. So they wrote the original equation again, which was very nice to do. Okay, and then they factored it just like you did, 2 sine x plus 1 times the sine x minus 1. And then, since that was the product equal to 0, you can split that up into either the factors happen to be 0. I would have put the word or here, not and. So 2 sine x plus 1 equals 0, or sine x minus 1 is equal to 0. I would just prefer or to and, because both have to be true, either one. So, on the first one, they subtracted 1 from both sides. They just didn't show it. Divided by 2, they didn't show it, but there they got sine x is equal to negative 1. And on the right, it was a lot easier. Just added 1 to both sides, sine x is equal to 1. So then you have to figure out what values of x make that true. Well, for sine x to be negative, you have to be the third or fourth quadrant. For it to have a value of 1/2, you have to have a reference angle of pi 6. So pi 6 plus pi is 7 pi 6, and pi 6 short of 2 pi would be 11 pi 6, just like you found. And then over there, the one and only place where sine x is equal to 1 in that interval 0 to 2 pi is pi halves. Okay, any questions? All right. Now they're skipping. Now they do show in the text. Why is it that every Tuesday and Thursday about this time, suddenly my eyes go dry and stuff? I was in this room all morning, no problem, but suddenly now my head's popping up, my eyes are getting dry. I don't know. Sort of bizarre. But on that last example, example 4, they have a graphical solution. They don't show in the text. I mean, they show in the text, but not on the slides. It shows those 3 zeros. Okay, one at pi halves, one at pi 6, 7 pi 6, and one at 11 pi 6. However, if you do it on a graphing calculator, it's not going to give you that in nice fractions of pi. It's going to give you decimal numbers. And unless you recognize that pi 6 is 1.5707, blah, 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 and, you know, the others I can't even begin to do, it's 3.665 is 76 pi and 5.760. I would never have said, oh, that's, of course, that's 11.6 pi. No, I don't know my decimal equivalents of fractions of pi that well. Okay. There is a checkpoint, as there is after every example, so please do your checkpoints as soon as you can. All right, oh yeah, I was going to move to example 5, but they don't have example 5, so let's do it here. Solve this one. Okay, different. That was 4, here's 5. 2 sine squared x, that sounds almost familiar. But this time it's a plus 3 cosine x. Yeah, I can't write. Minus 3 is equal to 0. How would you proceed on this one? Oh, good, there it's here. Top part of the alphabet was doing well, but now the bottom part of the alphabet is doing well. It's the middle part that we're missing. All right, this is example 5, bottom of page 365. We don't have it on the slide set, so we're doing it here
at the bottom half of example 4's slide. So where would you go from there? Oh, you're going to factor. Let's see how we would factor that. What's a little bit wrong? What's the problem with that? That would kind of be like saying, let's factor 2x squared plus 3y minus 3 is equal to 0. Can you factor that? No, because you have two variables in it. What's wrong with this one? You have two functions in there. You can't factor something with two different functions in it. So what are we going to do? Give up, throw up our hands, we quit? Can't do it? No, it's impossible. Or what you think? Does the square ring a bell? Pythagorean identity. Let's see if we can relate sines to cosines, especially using the Pythagorean identity. Can we?
What is sine squared x in terms of a Pythagorean identity? Or what is a Pythagorean identity that contains sine squared x? The basic one. Sine squared x plus cosine squared x is always, always, always equal to 1. So how can we isolate the sine squared x? Second? Yes, subtract the cosine squared x from both sides. Okay, these go away, and that gives you 1 minus cosine squared x. All right, let's go back to our equation here and do 2 times, instead of sine squared x, we're going to do a 1 minus cosine squared x, right? That's sine squared x, right? Plus 3 cosine x minus 3 equals 0. All right, now we got a little work to do. Yeah, but we like to work, right? Okay, what can we do? What should we do next? Yes, distribute the 2 across the parentheses. And what would that give us? 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. Now, there's a couple things I don't like about that equation. Anyone make a guess? Second?
Add up the single.
Okay, yeah, add up common like terms, and that's the 2 and the negative 3. Yes, we could do that. But what's the other thing? I really don't like my leading term having a negative sign. I mean, it's okay, it's fine, but I don't like it, you know. I cannot like it, right? So let's do first what Daniel said. We're going to add these two together, so that gives us a negative 2 cosine squared x plus 3 cosine x, and what do those two add to? Negative 1 is equal to 0. Okay, that's true. Okay, now, how can I deal with my next issue?
Switch sign.
Second?
Switch sign.
Yeah, and what do you mean by that? Changing all the signs.
Yeah.
And now really what am I doing? I'm multiplying both sides of the equation by minus 1 or dividing both sides of the equation by minus 1, whatever it's legal to do because of that lovely little 0 on the other side. I can do that with impunity, okay? So we'll make that a minus, that a plus, and make the middle one a minus. Now I used the magic of a magic pen here, so I didn't have to rewrite things. So I'm pretty lazy, right? Okay.
So, what do we do from here? Factor! Sounds like a wiener to me, okay? So we're hoping this will factor. If not, we'd have to use a quadratic formula, which I'd rather not, but let's see what we get. What's the only possible factorization for 2 cosine squared x? 2 cosine x times cosine x. Okay, and where do we look next? Sine of the last term is, what does that tell you about these two signs? Second? They have to be the same. And since the middle sign is negative, they both got to be negative. Okay? So that's a minus and a minus. Okay? And then the last question is really easy. What's the only possible factorization for what? 1 and 1. Okay. Let's hope we're right. But we don't just live on hope. We check it. 2x, 2 cosine x times cosine x is 2 cosine squared x. Yes. Minus 2 cosine x minus cosine x, sure enough, is minus 3 cosine x plus 1 plus 1. Yes, we have the correct factorization. Now what? Say that again. Okay, yeah, because of the zero product principle, we can say, I think I'll come over here and write it, either 2 cosine x minus 1 is equal to 0. For some reason, my pen's not writing. Okay. Or cosine x minus 1 is equal to 0. Now, let me go back and look real quickly. They don't give us any limitation on our x's. So we're going to have to assume the x's are all real numbers. So not going to have a limited domain like we did before. So that's just for the future. What are we going to do first here? For the first equation? Second? Subtract or add? Add 1 to both sides, okay? All right. That gives us 2 cosine x is equal to 1. Okay? Divide by 2, and that gives you cosine x is equal to 1/2. All right. Now the question is, what values of x do you need for cosine x to be 1/2? Value of that makes that true. Cosine x equal 1/2. I thought by now you know and love these ones that we use all the time. All right. Back to my circle again. I just don't have a lot of room. What I'm going to do is erase some of this stuff. We've already done the sine square. We used Pythagorean identity up here. So I'll get rid of it. And that led to this. Okay. I hope I erased the right thing. All right. Now, let's go back and do our first quadrant. Okay. Remember I told you the little rule for sine. The little rule for cosine starts at pi halves and goes down to 0. Cosine, this is the square root of 0 over 2. And this one up here is the square root of 1 over 2. The 45 here is the square root of 2 over 2. And this little one down here is the square root of 3 over 2. And this one, of course, is the square root of 4 over 2, which is 2 over 2, which is 1. So cosine of 0 is 1. Where is cosine equal to 1/2? 60 degrees, which in radians is pi thirds, exactly. So this is going to have x equal pi thirds, because all of your angles in the first quadrant are positive, and we need it to be positive. Now, let's go on and get the others, because there's no limit here. What is our period for cosine? Second. So period for cosine, same as for sine. Starts up here at 0, pi halves, pi, 3 halves pi, 2 pi. Okay, so we'll say plus 2n pi. Now, that's not just for positive n's, that's for negative n's as well, for any integer n. Okay, but is that the only place where cosine is positive? First quadrant. We know it's positive in the first quadrant. Where else is cosine positive? Fourth quadrant. And what would be the same reference angle in the fourth quadrant? Second. Second. It's 300 degrees. And what is that in terms of radians? Ooh. Well, let's think of it this way. It's, he said this is pi third radians here. Would it be 1/3 radian short of 2 pi? 2 pi is how many thirds? 2 is how many thirds? 6 thirds. So 5/3 pi. Exactly. 5/3 pi. So it would also be 5 pi over 3 plus your 2n pi. Of course, n can be any integer. For some reason, this is messing up. All right, let's go to the second equation. And what would that be? What do you do with that? Add 1 to both sides, and that gives you cosine x is equal to 1. And where is that true? At 0, okay? So x is going to be 0, but let's not write down 0. What is going to be the next one after that? 2 pi. So let's make it, well, let's just make it 2n pi, right? When n's equal to 0, you got 0. When n equal to 1, you got 2 pi. I've caught this thing is so weird. There's a little thing on my chair that loves to grab this cord and yank my computer onto the ground. So 2n pi. 0 plus 2n pi. This is just 2n pi. All right, that's what we got. Let's see how the book did. X equal 2n pi, x equal pi thirds plus 2n pi, and x equal 5/3 pi plus 2n pi. Got it. Any questions? There is a checkpoint there. The checkpoint has secant squareds and tangent squareds in them. Can you do it straight way that way, or what might you have to do? Yeah, Pythagorean identity to get it to work. All right. Well, also, they left off example 6. So let's now do example 6. All right, to erase this one? Okay. Ooh, where did that come from? Okay. Now we'll do example 6 on page 366. And this one has a little blurb under it saying, see LarsonPrecalculus.com for an interactive version of this type of example. So it may not be exactly this example, but it's one of this type. So here's the example. Find all solutions for this equation. Cosine x plus 1 is equal to sine x.
spaghettios. How are we going to deal with one like that? What's the potential problem of it? Sorry. Okay, I've got both sides equal sign. We can solve that pretty easily by subtracting the sine x from both sides. You get a 0 over there. But what is the other issue? Okay, with only x to the first power, I mean, your trig functions. No, all the Pythagorean identities have x to the squares. I mean, not the trig function squared, okay? But that is a good hint for what we should do, because there is no linear relationship between sines and cosines. There is the Pythagorean, which is a quadratic relationship. So then what might be your first step? Square both sides of the equation. Okay? Now, I say that, and as soon as I say that, I hear ding, 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 warning, warning, warning. Okay? Because when you square both sides of an equation, you should have alarms going off telling you that you might introduce what they call extraneous solutions. Okay? Because let's just say that the answer to this would be a, give me a number. Okay, I don't think that would ever be it. Okay.
2.
Yeah, let's leave off the squares. Let's go back to our original thing. What's the potential answer for this? Something between? Yes, so 8 wouldn't ever work. Okay, right. Okay. Something between -1 and 1. So pick a number between -1 and 1. Second? 1. Okay. All right. So let's say the answer to this was 1 and the answer to this was 1. Okay? Then that would be fine. When you square both sides, you still have 1 equal to 1. Right? But let's just imagine that this was a 1. This turned out to be, or this was a 1, and this turned out being a negative 1. And you square both sides, and you get 1 equal to 1. That looks like it's perfectly fine, but the original -1 equal 1 is not perfectly fine, because that can never happen. So you might introduce an angle that's going to make that second case true. This will still be 1 because it's -1 squared, or this one will still be 1 because it's -1 squared. This one will be 1 because it's +1 squared. Those are not equal. Okay, so basically what I'm saying is, anytime you square both sides of an equation, you've got to go back and check whatever answer you get, propose, and make sure it worked with the original equation, not just the squared equation. That was my little soapbox. Okay, now let's move on from there. Square the left-hand side. What does that give you? Cosine squared x plus, okay, I agree that's there, but we're missing something, aren't we? Plus what? Ah, yes, 2 cosine x. It's the square of the first, twice the product of the 2, square of the second. Okay. Or you can FOIL it and you'll get those same results. Okay? And we've got this is equal to sine squared x. Okay. Now we still have the problem of different functions. But now that we've squared, we can go back and use Sidney's idea. Yes, a Pythagorean identity, and which would be the easiest to use? We can go either way. It's the cosines to sines or sines to cosines. Which would you prefer? Sines to cosine, because that's just a single term there. And what does that give us? What is sine squared x? 1 minus cosine squared x. We already used that once today, didn't we? Okay? So we'll just ignore this one in the middle and go across here. So what can we do?
everything on one side and what on the other side? Nothing. Yeah, 0. Okay. So what should we do? Subtract 1 and add cosine squared x. It's the same thing you said, but to me it's easier to see this way, right? So I'm going to do the same thing here. I'm going to subtract 1 and add a cosine squared x there. So what does this give us? 2 cosine squared x plus 2 cosine, I can't write, x. That adds a 0, that adds a 0, that adds a 0. So everything's equal to 0. Now what might we choose to do? Or do we want it equal to 0 anyway? So we can factor, and how does that factor? How would you factor that, left-hand side?
First, you can take
Okay, I can't go. All right, okay, that is a good thing. Let's divide that by 2, that by 2, and that by 2. You still got 0. Not a bad idea, okay? Next. Yeah, factor out a cosine x. And what are you left with? Cosine x. Say again? Plus 1. And that's equal to 0. Okay? And where could you go from there? Okay, so either cosine x is equal to 0 or cosine x plus 1 is equal to 0. Now, where is cosine equal to 0? And again, let me go back and look at the problem here. They have no... Oops, yeah, it is. It's on 0 to 2 pi. This is on 0 to 2 pi. I like that better, to have some sort of limitations on it. Find all solutions for that original thing on 0 to 2 pi. Okay? Now, where is cosine x equals 0? What value of x is cosine x equal to 0 between 0 and 2 pi? Pi halves and 3 pi halves, okay? So this is either going to be x equal pi halves or 3 halves pi, okay? And the second one here, what would that be? What do you do first? You can't factor it. It's what? Oh, subtract 1. I thought you said factor. Subtract 1 from both sides, and that gives us equal -1. Now, whereas cosine x equals -1 between 0 and 2 pi. At pi, exactly. So there would be x equal pi. Okay. But what we have to do here, because we squared both sides, we go back to our original equation, which was cosine x plus 1 equals sine x. And let's plug in these 3 values and see if we get equalities. We may or we may not. Let's see what happens. Let's plug in pi halves first. What's cosine of pi halves? Second? 0 plus 1. And what sign of pi has? One. 0 plus 1 is equal to 1. That one checks. Good deal. Okay, let's do the next one. Cosine of 3 halves pi plus 1. Is that equal to sine of 3 halves pi? Okay. What is cosine of 3 halves pi? 0 plus 1. Is that equal to what sine of 3 halves pi? -1. And guess what? The square of those are equal to each other, but they're not equal to each other. So you see, we did introduce an extraneous root here, at least one. 3 halves pi works for the squared equation, but doesn't work for the original equation. So this one is not true. We still have one more to do. We'll say cosine of pi plus 1. Is that equal to sine of pi? There's the next question. What's cosine of pi? -1 plus 1. Is that equal to what sine of pi? 0. And guess what? Ding, 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 it is. So this is also an answer. So 2 of the 3 were correct solutions. The third one was an extraneous solution. It worked for the squared functions, but didn't work for the original functions, which were not squared. Okay. So they got x equal pi halves and x equal pi. Good for them. See, these were a little bit more involved examples, and yet they put the very easy one on the slide set and left off the other two. I think it's a good idea to do them all. Okay, any questions? Move on to, yes? Sure, yeah, anytime. Is this for good or just for temporary? For good, okay. Not feeling well? Yeah, okay. All right, let's move on to functions involving multiple angles. Now, just a little bit of a, they may say it here. If you think about what we did when we have equations here, especially of the quadratic form, okay, we treated the function as if it was a variable, solve for the function, and then solve the function, okay? Now, when you have multiple angles, we're going to do the same type thing. We're going to first solve for the trig function, then we're going to solve for the argument of the trig function, which is going to have multiple things, and then we're going to solve for the variable. So we have 3 steps now rather than 2. Back in just quadratic equations, we just had solve for x, okay? Then we went to solve for functions of x. Now we're solving for multiple functions of multiple x's. The next example involved trig functions with multiple angles of the form cosine ku and tangent ku. You could have sine ku too, I don't know why not. To solve equations of these forms, first solve the equation for, okay, I'm going to interject stuff. First solve the equation for cosine ku, then solve the equation that you have from that for ku, then solve the equation for u, okay? Divide by k to get what u is. So it's a real simple last step, but you got to take it. You can't ignore it, okay? So here's example 7. Here's your equation. Solve this. 2 cosine 3t minus 1 equals 0. How would you go about solving that? Say again? Add 1 to both sides. You first solve for cosine. So you add 1 to both sides, and that gives you 2 times cosine of 3t, those add to 0, is equal to 1. Okay, now what? Divide by 2, because you're solving for cosine. Okay, so that gives you cosine of 3t is equal to 1/2. Okay, now you solve for cosine. Okay, so now we figure out what values 3t must take on that the cosine of that would be 1/2. And we kind of already done that today once. Can anyone remember what they would be? Where is cosine equal to 1/2? Pi thirds, okay? That's at least one. So we have 3t equal pi thirds. And what's the period for cosine? 2 pi, so that would be plus 2 n pi. Because they didn't give us any restrictions on this, so we have to include that. But is that the only place where cosine of 3t would be positive? You know in the first quadrant it is 5/3 pi too, also, because that's going to say 3t, or 3t is equal to 5 pi over 3 plus 2n pi, because the period of cosine. All right, but I really don't care what 3t is. I want to know what t is, okay? So we first solved for cosine, then we solved for 3t, now we solve for t. So what do we do here? Divide everything on both sides by 3. So that would be t is equal to pi ninths plus 2/3 n pi, or 2 pi over 3 times n, however you write that. Here you do the same thing, divide by 3, divide by 3, divide by 3, and that would be t is equal to 5 ninths pi plus 2n pi over 3. There you have it, however you want to write that down. Okay? So it's just one more step. Okay? First solve for the function, then solve for the argument of the function, then solve for the variable. Okay? That last step is just dividing by whatever your multiple was. Okay? So, all right, for me to erase this, you got down what my answer was. Let's see if they got the same thing. Okay? First thing they did, they wrote down the original equation. Oh, what a good waste of time. Good thing to do. Okay? Then they subtracted or added 1 to both sides. They got 2 cosine 3t is equal to 1. Then divided both sides by 2. Get cosine 3t is equal to 1/2. You've now solved for the function. Okay? Now we try to find values that make that true. So you solve for 3t. That makes 3t either pi thirds plus 2n pi or 5/3 pi plus 2n pi. Exactly what y'all got to. Now we divide both sides of both equations by everything on both sides by 3, and that gives you t divided that by 3. Pi thirds divided by 3 is pi ninths, and 2n pi divided by 3 is 2/3 n pi. And same thing over there. 3t divided by 3 is t. 5/3 pi divided by 3 is 5 ninths pi, and 2n pi divided by 3 is 2/3 n pi. Good deal. There's your general solution for any n. Positive, negative fraction. Positive, negative, or 0. Okay. Make sense? All right. There's a checkpoint there. Do your checkpoints. That's actually a little bit different one. Still coming up the same, but it's not one that we had done like it today, so good idea to do that. Let's see, they do not show example 8, so let's do example 8 here. This was the tangent one they said. Ha, good. 3 times the tangent of x over 2 plus 3 is equal to 0. What would be the first thing you choose to do? Subtract 3 from both sides, is that what you said? Okay, I agree. Sounds like a good thing to do. All right, and that would give us 3 tangent of x over 2, that goes to 0, is equal to negative 3. Now what? Divide both sides by 3. Sounds like another good thing to do. What would that give us? Negative 1? Okay. All right. So now we have that the tangent of x over 2 is equal to negative 1. Okay. We first solved for the function, the tangent. We got that. Now we solve for the argument of tangent, the x over 2. Now, what angle, x over 2, when you take the tangent of it, do you get negative 1? Tangent of what angle is equal to negative 1? Do you think better with the unit circle or with the graph of tangent? They both are pretty straightforward. Which do you think you'd see better?
It's 3 pi halves, like 3 times pi, 7.
Okay. Are you doing the whole thing now, or are you just doing the x over 2? If this was a tangent of theta is equal to negative 1, what would your theta be?
Pi halves.
Pi halves tangent is actually not defined. Because tangent is sine over cosine, and pi halves cosine is 0. You can't ever do that. Vertical asymptotes are your half pi's. That's why I was asking if you see the graphs of the functions better or the unit circle, either one.
I think it's 3 graphs better.
You do? Okay. So let's do the graph of tangent. Okay. Tangent function basically is like this, right? Vertical asymptote here at minus pi halves, and vertical asymptote here, I should be doing those in red, at pi halves. Okay, so your function is positive in the first quadrant and negative in the fourth quadrant. First quadrant is between 0 and pi halves, fourth quadrant between negative pi halves and 0. So you got to be somewhere to the left of origin. Where is it negative 1? Kind of did that artificially. I tried to get it so it looks like it's exactly. Say again? No. Okay, where this is negative 1, the value is negative 1, what angle is that going to be? I tried to do it so it looks like it's exactly halfway between there. Pi fourths, negative pi fourths, okay? Negative pi fourths, I'm sorry, x over 2 is equal to negative pi fourths. Right. Now, here's why. This is why I asked about the unit circle as well. Remember what tangent is on the unit circle? What was it on the unit circle tangent? Y over x. No, x over y. Right. No, tangent is y over x. Opposite over hypotenuse. Taking oats away, right? Okay. So it's the opposite over hypotenuse, which is y over x. For that to be minus 1, you must be on, where that is plus 1, you're in the first quadrant, right? Y is the same as x, so you're on the diagonal line here. In the third quadrant would also be plus 1. It's the second. In the fourth quadrant, you would be a minus 1, because your y is negative and your x is positive, while y is positive and x is negative. Okay? Let's say in the fourth quadrant, because that's the fourth quadrant here, that's going to be at your diagonal this way. And that's going to be at minus 5/4. Right? That's where you think. What's that? Opposite over adjacent. Yeah, that's what I said. The opposite value is your y value, adjacent value is your x value. Right? On the unit circle. Right? And that's where these are opposite. They're the same value but opposite signs. And this would mean a negative unit circle, negative value here, positive value on x, negative value on y, but the same value, so it must be on that diagonal right there. And that diagonal is minus 5/4. Right? So, now if you don't like negatives and you want to make it positive, just add 2 pi to that. What would that give us? I don't know, you may like negatives on that. What would that be? Again, the system, that would be pi/4 short of 2 pi. Would be how many fourths pi? 8? 7. 7 fourths pi. So let's write it this way. So pi halves, x over 2 is equal to 7 pi fourths. Now, what is the period for pi? It's the period for tangent. Is pi plus n pi. Now, I really don't like this either, because it is fine. We'll see how the book did it. This could either be 7/4 pi, or it could be the one up here, which would be 3/4 pi. Right? So it's going to come around and go around and around. So you could make that 3/4 pi also. Those are the same answers because you're adding n pi to it. So let me just look and see which one the book is going to do. Yeah, they do the 3/4 pi. Okay. Usually you don't, but you don't usually use 7/4 pi either. I would have normally used -1/4, but I didn't think the book was going to do that. 3/4 pi. This time we're up here rather than down here. There's still -1 there, right? Okay. So, this is on unit circle type thing. So that's what x over 2 is. But I don't really care what x over 2 is. I want to know what x is. So what are we going to have to do?
Multiply by 2.
Yes, multiply everything on both sides of the equation by 2. Okay? So that becomes x equal to, 2 will go in the 4 2, so it would be 3 halves pi plus 2 n pi. There's your answer. Okay. This only gave us 1, so sure enough, that's what we got. So let's see what the book got. 3 halves pi plus 2 n pi. And then they have another checkpoint at the bottom, which is a fairly similar problem. In fact, no, it's not quite the same. Almost the same, but not quite. Okay, now, what we've been doing so far in solving these equations
is when we know that solution really, we recognize it. For tangent, plus or minus 1, for sines and cosines, root 2 over 2, root 3 over 2, 1/2, all those kinds of things. We know those. Those are our 0, pi 6, pi halves, pi quarters, pi halves, pi thirds, and pi halves. We know those. I thought we did anyway, okay? But a lot of the times, we don't have that luxury. We have weird things that are not those common ones. And then we have to use inverse trig functions to do our solutions. Here is one type example. Okay? This is example 9. They didn't give us any lead-in. There's our equation, original equation. What in the world do we do with that? Yes, okay, you've got two different functions there. You can't solve an equation for two different functions, so you got to get them both to either be tangents or both secants. And since the secant is squared, and the secant squared is related to tangents by the Pythagorean identity, let's get that into tangent squareds. So, what is that Pythagorean identity that relates those two? X, we'll put it, is equal to secant squared x. There it is right there. So instead of secant squared x, we're going to write 1 plus tangent squared x. Oh, they made it easy for us, didn't they? Minus 2 tangent x. Now what else had we better do here? I should have looked at this first, but I didn't even think about it. I was just focused on the other. Yes, we subtract 4 from both sides, and that's going to give us minus 4 equals 0, because we want that to be a 0 over here. Now, what else do we have to do? Yes, combine like terms, and that gives us tangent squared x minus 2 tangent x minus 3 equals 0. All right, next. Factor, yeah, sounds like a winner. And what's the only possible factorization for tangent squared? Tangent x times tangent x. Okay? Then where do we look next? Sine of the last term, which is negative. What does that tell you about these two signs? They have to be opposite. So 1 plus and 1 minus. Doesn't really matter what you put here because tangents are equivalent. Okay, and then what's the only possible factorization for 3? 3 and 1. Which you want to put with what? Okay, 3 with the negative and 1 with the positive. I think you got it. Let's just check it and see. Tangent times tangent is tangent squared. Yes. Minus 3 tangent x plus tangent x. That would be minus 2 tangent x. And then a minus 3. Yes, we got it right. And what does this give us? Where do we go next? Okay, so either tangent x plus 1 is equal to 0, or tangent x minus 3 is equal to 0. Okay, what does that first one tell us? What do you do for next? Subtract 1 from both sides, and that gives us tangent x, that adds to 0, is equal to negative 1, or add 3 to both sides, and that gives us tangent x
is equal to 3. All right. Now we have to think about what angles x, when you take the tangent of it, do you get a negative 1? Second? Pi fourth. Pi fourth, only that would be a positive 1. So that's in the first quadrant. So the second quadrant, that would be fourths less than pi. Three pi fourths. Yeah, we had it before. 3 pi fourths. So here x is equal to 3 pi over 4. And then what is the period for tangent? Pi, so it's plus n pi. I don't think they gave us a limitation on this one, did they? No, they didn't. Okay? But how about at what angle x is tangent equal to 3? Why not? What's that? Now, if that were a sine or a cosine, you'd be absolutely right. It's not. Because sine and cosine can never be outside plus or minus 1. But tangent, remember the graph we had before? It goes from negative infinity to positive infinity. So yes, it is a legitimate angle, and it's something on the positive side, okay? But it's not one of our favorite little angles, because those all had root 3s, root 2s, it had something in it, nothing. So what you have to do here is take a inverse function. Remember them? Take the inverse tangent of both sides, and inverse tangent of tangent is just going to leave you with x, and that's going to be inverse tangent or arctangent of 3. We don't know the angle. Just do an inverse tangent. Okay? But then you still have to do plus n pi. Okay? Even though you don't know what angle that is, that's how we do it. Okay? So, let's see how they did it. They like arctangent. That's just extra writing to me, so I do it inverse. All right, for me to erase this. Okay. And that is going to first, instead of secant squared, put 1 plus tangent squared minus 2 tangent x minus 4 equals 0. That gives you tangent squared x minus 2 tangent x minus 3 is equal to 0. Factor that, you get tangent x minus 3 times tangent x plus 1 equal to 0. Set of each factor equals 0. You obtain two solutions in the intervals negative pi halves to pi halves. And the first of these, you can't do anything else with. It just is x is equal to arctangent of 3. They just skip everything in between. It's tangent x equal 3, then take the inverse tangent of both sides. X equals arctangent of inverse tangent of 3. Now, on the other side, you know that's got to be negative pi halves. Okay? To be within this. And that's why I said on the previous one, that's what I would have gone for, but I didn't think they did. But now they are going for that. And I don't know why they allow a negative in one place and not in the other. It doesn't really matter. So on both of those, whatever the angle arctangent 3 is, add n pi to it. Okay? And whatever the angle x, negative pi fourths, add n pi. Which is exactly the same thing as 3/4 pi plus n pi. Because the n is any energy. Okay? So the general solution you could either write as
minus n pi fourths plus n pi, or 3/4 pi plus n pi.
All those are the same answers.
Because if you think about it, 3/4 pi is pi plus n negative 1/4 pi. Yeah. Close. Yeah. So. All right. You can use your calculator to approximate the value of arctangent 3. Okay.
Be sure you're in radian mode, though. Okay. Now, we did run out of time. Sorry about that. We still have examples 10 and 11 to go. However, I just noticed they're not on the slide set. So I'm going to start with 5.4, but we're going to do the examples 10 and 11 first. So let me make your homework assignments here. Any of the odds 5 through 9, they're all at calcchat.com, none of them at CalcView. Any of the odds 11 through 27, there's a whole passel of those. They're all at CalcChat, only 13's at CalcView. Any of the odds 29 to 37, they're all at CalcChat, 29's at CalcView. Any of the odds 39 to 45, they're all at CalcChat, 39's at CalcView. Do number 47. It's just sort of a pretty straightforward exercise. Don't try to make it anything worse than it is. Then the odds 49 to 57 are saying use graphing utility to approximate those. I think most of them you can do the way we just did that last one. And I believe you can do any of the odds 59 to 69, similar to what we did in the last one. They're all at CalcChat, 61's at CalcView. We haven't done one with the quadratic formula yet. Yeah, that's example 10. So stop there. We'll do the rest of those after we do example 10. Okay? Good deal. Is Sarah sick today, or do you know?
I think so, yeah.
I'm sorry.
I was sick last week, and I think I gave it to her.
Oh, no.
Yeah.
I knew she said you were at the doctor's, so I wondered. Okay, well, we'll see you Thursday.
Thank you.
All righty.